Hello everyone. Today I want to talk about harmonic series for you. First, let me explain where this name is coming from. Okay, for those who play music or play any kind of instrument, string instrument or wind instrument, doesn't matter. You know that when you want to play like a note with any kind of instrument, usually you don't create only that note. Let's say, for example, if it is some string instrument and this is the wave that it is created because of hitting like a string, not only some sound with this wavelength is created, all different sounds with the frequencies which are multiples of that, let's say twice as big or 3 or 4 or 5, also usually they are created. Or you can say the wavelength of this one is half of this, wavelength of this thing is 1/3, wavelength of this is 1/4 of that, etc., etc. This is usually it's called fundamental. Let's say when you play a note C, this is that. These are the two, which is twice as big as that, the frequency. This is usually called harmonic. And when you multiply this 2 by 2, that would be 4. So you create this one, which would be another C with a higher pitch. And the other ones are the other notes. So this whole series of different multiples in terms of frequencies of the fundamental, these are called harmonic series, and usually these are called overtones of that fundamental. Okay, so if you look at the wavelength, let's say if this is 1, this is 1/2, this is 1/3 of that, so that's 1/3, this is 1/4 of that, all that stuff, right? Called harmonic series. Now, how is this related to this mathematical problem? Now, let me explain another example that again is idea of harmonic series appears in that example, and then a third example in here, and then I try to explain the mathematical theory of that. For example, think about, let's say you have a table and you have a bunch of blocks. This could be like dominoes or anything like that. Okay, let's put this, the first domino, on the table like that. Question is, how much can you push this thing to the right, this block, such that this block still stays on the table and doesn't fall down, right? Obviously, if you start pushing this thing and this thing to the right, up to here, when this is almost, let's say this is 2 feet long or 2 inches long, when this gets to this point, if you push more, this falls down. Basically, the center of gravity of this block must stay above this, right, for this to stay stable on the table. Otherwise, it falls down. So you can say if this is 2 feet, for example, you can overextend this thing by how much? By 1 foot. Or you can call it overhang, right? This overhang. Now let's say you want to put another block on that. So you bring another block and you want to put that block underneath this thing and push that block now to the right, such that this stays on the table and doesn't fall down. When you put that thing underneath this one and then you push it, there would be, you can push it up to here. In physics, you can prove that this length would be 1/2 of the foot. So that was already 1 foot in here, and you put this block underneath that, you can slide this thing up to this much, right? To just make sure if you do more, this bit would fall down. So far, our overhang would be 1 plus 1/2 this much. And you can continue doing that, right? Let's say you have 20 blocks. How much of overhang can you get? Again, you want to put another block underneath these two and then push it, right, to get a balance before this just falls down. Then, as I said, you can prove that this can go up to 1/3 of whatever the unit is, foot or inch to the right side. And so this, you get this much overhang, 1/3. And you can continue doing that. 1/3 plus 1/2 plus 1. If you have another block, that would be another 1. On the next one would be 1/4. And keep going. Every time this structure moves a little bit to the right, and the question is, how much this goes to the right? Would be a finite amount no matter how many blocks. Now let's say you have infinitely many blocks and you want to keep this structure still stable. How much of overhang means from the edge of this, how much it can go to the right? Is it just a finite amount? Or this can go forever, right? So how much overhang you can get? So obviously in this case, what do we have? What's your overhang? It is 1 plus 1/2 plus 1/3. When you bring the next block, that would be 1/4 plus ... Such a thing is called a harmonic series. And the problem of convergence of harmonic series means if you add infinitely many of these terms, means plus 1/5, plus 1/6, plus 1/7, and you continue forever, is this a convergent series, means you get a finite number, or you get an infinite number, right? Which one? So this is the main problem about harmonic series. Okay, do we have any other example? Sure, this is another example that I can show you. Imagine that you have some elastic band, like a wristband, right? Something circular. And at time 0, let's say you have some ant in here. Let's say the circumference of this is 1 meter, right? And this ant moves with the speed of 1 centimeter per second. That means in 1 centimeter, this ant goes, because 1 meter is 100 centimeter, and so that means in 1 second, this ant travels by how much? By 1 centimeter. So from here goes to here, okay? Now, assume this is the case that this circular band, every second, its length would be extended by 1 meter. That means if it is 1 meter now, after 1 second becomes 2 meter, the circumference of that. After another 1 second becomes 3 meters, 4 meters. So with a rate of 1 meter per second, the circumference of that grows. The question is, okay, so obviously the ant feels that under his feet this is moving, and the more it goes, it seems that this goal, which is reaching this point again, is getting farther. Question, can this ant ever go one complete round and reach this point again? It seems that every time, let's say, the ant goes this much, let's say, for example, 1 meter, and this is extended, and you may think, no, this never reached this point, but the answer, in fact, is yes, right? But look, what's this problem mathematically? How can you write it? First, the ant goes 1. Let's say 1%, this is 1 centimeter of 1 meter would be traveled after 1 second. You can say it's 1%. So the ant travels 1% of the whole way. Then in the next second, because this adds by 1 meter becomes 2 meters, right? Then in the next second, the ant goes just 1 centimeter, and this thing is 2 meters. So 1 over 200, or you can say it is 0.5% of this whole thing is traveled in the next second. And in the next second, again, 2 meters becomes 3 seconds. And this becomes, of course, it becomes, and the ant still goes just 1 centimeter per second. So it is 1 over 3 meters, which is 300 centimeters. So it's 1/3 of percent, right, of this would be traveled by the ant, and this keeps going. Again, what you see? You see the same problem. So the problem of harmonic series. So the answer, okay, is if after you add enough terms to that, at any point, this reaches 100, which is 100%, this number becomes 100, that means the ant can complete one turn and reach this point again. But if this is a finite kind of sum, that, for example, no matter how many terms of that you add, let's say if it never goes beyond 6 or 7, that means the ant cannot finish more than 6 or 7% of the whole travel. Okay, so that's another example. These are all different examples that you see harmonic series in. Yeah. Okay, so our main question is then, is this divergent or convergent? Okay, so let me turn this 180 degrees, guys, and let's take a look at this is stuff on this side of the board. Okay, now, so I have my harmonic series in here, 1 plus 1/2 plus 1/3, 1/4, 1/5, dot, 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 this continues. Okay, question, is this convergent or divergent? Okay, first of all, let's consider sub-series of this one, which is easier to figure out if it is convergent or divergent. That means just pick some of these terms. Let's say term 1/2, terms 1/4, terms 1/8, terms 1/16, dot, dot. This is a sub-series. Just we pick some special terms of that and we add them. Let's see if this is finite or it is not finite. This is a much simpler example to argue. So we want to discuss this thing. Is this finite series or not? There is some easy geometric way to show the convergence of this series. How? Okay, consider this square is 1 foot by 1 foot, so total area is 1 square feet, right? So let's consider, let's assume that you take half of this and you paint half of this square. So what is the area this way that you paint? Of course, this is half of 1 square foot would be 1/2. So it's half a square foot of that is now painted. Now you take the other half and again, you divide it into 2 equal parts and you paint this thing. What's the area of that? Of course, it's 1/4, right? So you added 1/4 to that, 1/2 plus 1/4, right? Then you keep going and you take this white area and you paint half of that. That's what? That's 1/8. So far the total painted area is 1/2 plus 1/4 plus 1/8, and you keep going. That means this is, you add this thing is 1/16, you add this thing is 1/32, you add this thing, this is 1/64. So that means it seems you are adding more and more terms of that. So eventually, when you continue this forever, is there any part of this area which is not painted? Not really. Everything will be painted. And when you are done, let's say if you have infinite time, the whole surface of that is covered. But what is the total surface of that? Of course, is 1 square foot. So that means this sum is equal to 1. Okay, so it seems this sum is convergent. and it converges to what? 1. What does it mean? That means the more of these terms that you add together, the sum that you have becomes closer and closer to 1. Number 1. Okay, so this is convergent. How about that one? This is a little bit harder than that, but there is an easy and cool way, in fact, to figure out this. Okay, let's look at this black harmonic series that we have on top and compare it to another series. This is a way to check the convergence or divergence of series. Compare them with other series that you know they are convergent or they are not. Look at this one. 1/2, look at these two terms, 1/2 and 1/3. You agree that 1/2 and 1/3 are bigger than 1/4 and 1/4, right? So make this series, put 1/4 and 1/4, and keep in mind that these two are bigger than these. Then you have 1/4, 1/5, 1/6, and 1/7, right? So compare these with 1/8, 1/8, 1/8, 1/8, 1/8, 1/8, right? Obviously these four are all bigger than 1/8, right? So then go for the next. So these four, look, 1/4 plus 1/4, that becomes 1/2. 1/8 plus 1/8 plus 1/8 plus 1/8, this thing is also 1/2. And then you go compare the next 8 terms, means 1/8 to 1/9, 1/10, 1/11, 1/12, 1/13, 1/14, and 1/15. You compare it with 1/16. They're all bigger than 1/16. How many of these 1/16s we have? We have 8 of them. 8 1/16. That means some of these next 8 would be 1/2. And you can keep going like that. So compare this with this. Obviously, every term of this from 1/2 is bigger than all these. But what is the sum of the red series? As I said, this is 1/2, this is 1/2, this is 1/2. So basically, you are adding infinitely many 1/2s, which is of course not finite. It is an infinite number. So this series is an infinite series, right? So obviously this series, which each term of that is bigger than the corresponding term of this, which is bigger than something infinite, that's definitely infinite. So that means this is a divergent, this harmonic series that we were interested in, that's divergent. Okay, this was convergent, but that thing is divergent. Okay, that's basically now we proved something mathematical. But this is the nature of, in general, science and math. When you do a problem, usually you don't say, okay, I'm done, so goodbye. Usually you ask the next question, and the next question, and the next question. So the next question is okay. So by that means, do you remember that problem of overhang? Right? So what does it mean? That means if you put these, you have infinitely many blocks, and you put them that way, this goes forever. So that the overhang would be infinite. Or about the ant, can that complete this? Yes. Because without bound, this gets bigger and bigger and bigger. So that ant definitely at some point, at some time, it would be some time which is bigger than the age of the whole universe, but at some point reaches that starting point again. Okay, but next question is how fast this thing grows. Because when you add these, it may grow very fast, or it may grow very, very slowly. The fact is that series is very sluggish, in fact. It goes very, very slowly. Okay? Now, the question is how slow? Let's investigate that. Look at this one. Consider the function y equal 1/x that I have graphed it with black. This is a black graph over here, right? Look at this one. This is 1, 2, 3, 4, 5, and we continue this. Okay? Now, look at the area of this rectangle in here, this is 1 and this is 1. So the area of this rectangle in here, 1 times 1, which is 1, plus, what is the area of the second one, this one? This is 1, and this thing is 1/2, because the value of this function at 2 is 1/2. So 1 times 1/2 is 1/2. So the area of this rectangle plus this rectangle is that. And what's the area of this one? This is 1/3 times 1. So area of this rectangle is 1/3. And the next thing is 1/4 plus dot dot, right? Dot 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 dot, right? Now, I want to compare, look, now I want to compare this area, and let's say you go up to the point N. So you have dot dot dot, let's say that you continue these rectangles up to the point that this thing is N. So that total area is 1/n. But now, look at the area under this black curve. Look, those who had a Calc 1, they know the area under a curve is the integral of that curve. So this curve is 1/x. The integral of that from what? From 1. Right? Look, this is 1, 2, 3, 4, 5. This is your fourth one. What's the endpoint of that? Is 5. Right? So if you go n of these, always the endpoint of that thing is 1 more. So it is n plus 1. So obviously this area is what? This area is bigger than the area under this curve. Right? By how much? By these, you see these shaded red areas? This is the difference between the area of that and the area under those. So, then, if you find the area under this and you add some number to that, that becomes then this area. Okay? Now, first of all, those who passed that Calc 1, they know that this integral is ln of x. It is ln of x from 1 to n plus 1. So I write it this way. ln of x from 1 to n plus 1. What is that? If you put n plus 1, this is ln of n plus 1 minus ln of 1, which is 0. So this becomes ln of n plus 1. What's that? That's area under the black curve. And this thing is the area under this. And we said that if you add something to this area, which is their shaded area, you get exactly this area. So if I add a number which is called gamma to this, then this becomes exactly equal to this. That means the difference between this and ln of n plus 1 is gamma. How big is gamma? Gamma is called Euler constant, and it is very important constant. It amazingly plays an important role in different areas in mathematics, in physics, in quantum physics, almost in many different important phenomena in the nature. It shows up. How big is gamma? I said it is just this shaded red area. Look, assume that I move all these shaded areas to this. Right? This one is this. This one is this. This one is this. This one is this. What do you see? That does not even cover the whole 1 by 1 square that I have in here, right? So if the area of that is 1, so this total area, this purplish thing that you see, would be less than 1. So that means this gamma, which is exactly this shaded purple area, is less than 1. In fact, it is something around 0.57. That's the value of gamma. Gamma is something like pi. Of course, you can continue getting better and better approximations for that. Okay? The point is, gamma is really, really important constant in mathematics and physics. And if you want to know more about it, probably you can watch and listen some more videos regarding this gamma. If time allows, we try to do that in the next videos. Thank you so much, and you have a great day. Thank you.